So thanks everyone. That concludes our contribution talk session. Now we'll commence with our second invited speaker session. And the speaker is Professor Eiji Uchibe. Eiji is a principal researcher at the Department of Brain-Robot Interface, ATR Computational Neuroscience Labs. He earned his PhD in mechanical engineering from Osaka University and has held a position of research associate at the Japanese Society for the Promotion of Science. He has published over 100 research works spanning robotic learning, reinforcement learning, evolutionary computation, computational neuroscience, and their applications. Welcome, Professor Uchibe.
Yes, thank you for the invitation. So it's my great pleasure to present our work here. So title is Human in the Loop, Machine Learning by Co-evolution of Human and Genetic Imitation Learning. So let him start what reinforcement learning is. So maybe you are familiar with it. But anyway, so I'm working on reinforcement learning. So this figure illustrates the interaction between the learning agent and the environment. And as you know, so when we apply the reinforcement learning to the system, so one of the major issues is that how we design the reward functions. So it means that if reward function is not correct, so so even though learning algorithm is perfect, so learned behavior is not our intention one. So for example, so let me explain the two examples. So this task is to move this mobile robot to get the battery pack. So in this case, so when robot get the battery pack, so it can charge and it's treated as a positive reward. And as you know, so as you can see, so there are no obstacles. So it's very toy problem, but so if we use a very sparse reward, it eventually learns a battery catching behavior at the end, but it takes very long times, even though this task is simple. But then, so to accelerate the learning, so we add some image-based rewards. For example, so in this case, so when robots see the battery pack, so robot receives a small positive rewards according to the direction of the battery packs. And then so we consider the weighted sum of the original reward and weighted of sub-rewards. But in that case, sometimes if weighting is not good, so the robot failed to learn the battery catching behavior. It means that so sometimes robots just learn to watch the battery packs. So it's quite different from our intention behavior. So in that case, so even the task is simple, so it's quite difficult to design the reward function. And this is a this is a second example. So the task is to this upper body human robot to fold T-shirts. So in this case, in this study, so we did not use a simulator at all. So therefore, so we developed a kind of a sample efficient reinforcement learning with entropy regularization. But at the end, so we can achieve this kind of behavior of holding T-shirts. But to learn this behavior without using simulators, so we have to prepare very well-designed reward function shown like this. So roughly speaking, so it appropriately provides a sub-rewards according to the progress of the learning. So it means that so robot learns some behaviors automatically, but we have to design the reward function carefully. So then, so we are now interested in the imitation learning that is derived from the combination of the impulse reinforcement learning and the forward reinforcement learning. So then, so let me explain what imitation learning is. So imitation learning is learn to how to act given a set of demonstrations provided by the human experts. So like this, so human control some this kind of these robots, and then so robot learn to mimic the expert behaviors. So formally, so this kind of imitation learning is formulated by minimizing some distance between two distributions. One is the expert distribution and the other is the learner distribution. So based on some distance metrics, so we can learn some imitation learning policies. So then, so one of the approaches is generative adversarial approaches. So that is so to minimize the object function, because we do not know the object function explicitly. So at first, we have to estimate the distance between the two distributions from samples. Then, we have to minimize the estimated distance. So the first part corresponds to learning the discriminator. The second part corresponds to learning the generator. So in the terminology of the reinforcement learning, so the first part corresponds to the inverse reinforcement learning, and the second part consists of forward reinforcement learning. So based on this framework, so mainly we working on several projects. One is a human in the loop imitation learning, and the second is a multitask imitation learning, so which has multiple tasks. And the third one is a kind of cross-domain imitation learning. So today's topic of today's workshop is a human in the loop learning system. So therefore, we focus on the first part of this section. So then let me explain the overview of our human in the loop imitation learning. So which consists of mainly 4 parts. So first is a expert data collection as usual, and second part is a offline model-based imitation learning, which is core of our generative adversarial imitation learning in the study. So the third one is a kind of a generate trajectories by learned policy in the previous steps. Then the fourth step is a reward learning from preferences, that is from the demonstration provided by the imitation learning module. So human assign the levels, then go back to the imitation learning part. So by iterating these processes, learning systems and human can evolve simultaneously in some sense. So actually, so the first part is very common, and so therefore we skip the detail of the first part, and so let me explain the second part. So second part is the offline model-based imitation learning. So at first, in the first part, expert data is provided by the human expert. Then the goal is to learn or mimic the expert policies. But in the framework, so we learn not only the policy, but also the environmental dynamics simultaneously from the expert data set. That is the objective is to learn the policy and state transition probabilities. So to achieve this, so in the method, there are 2 discriminators. One is a policy discriminator, as usual, and second is a environmental discriminator. The most important thing is that these 2 discriminators are represented by the component of reinforcement learning. That is, so we do not use as naive discriminators. So the point is they are given as a function of reward, state value, action value, and policy and state probability models. So therefore, it means that training the discriminators, so we can estimate the reward function and value functions at the end. So policy and state dynamics are improved based on the trained discriminators. So those frameworks are basically built on top of the generative adversarial networks, but to derive this algorithm, so we employ the entropy regularization of policy and dynamics. I do not explain the detail, but most important cellular part is that, for example, the goal of the policy discriminator is to distinguish whether the state action pair comes from distinguish whether the state action pair comes from the expert demonstration or is generated by the agent. Then, so this equation shows the specific form of the discriminator. So that important thing that so this discriminator is presented by the action value function, state value function, and current learner's policy. And there, this discriminator has two hyperparameters, alpha and beta, that control the accuracy of the discriminators. And also, it's also related to the forward reinforcement learning part. And during the training of the discriminator, so the learner's policy is fixed because learner's data is generated by this parameterized policy. Therefore, we don't need to train this policy during the learning of the discriminators. So it means that so it learned during the training. So during training, action value and state value are updated. And we use a cross entropy loss, which is regularization loss. And so this regularization is a bit somehow specific because, so as I said before, so our discriminator is derived from the entropy regularized reinforcement learning. So therefore, so there are some relationship between Q and V functions. So this complicated equation assures that the state value function V is a normalizer of the Q function to derive the stochastic policies. And second discriminator is the environment one. So the goal is this environmental discriminator is to distinguish whether the type of state action and next state comes from the real environment or is generated by the model. So similarly, so this discriminator is represented by the reward, state value, and action values and models. So, and similarly, so during the training, so this environment model is fixed and reward and value functions are trained. Of course, we can use a cross entropy loss with regularization. So this equation shows the regularization term. I do not explain the detail, but important thing that so this corresponds to the soft Bellman equations. So it means that so, as I said repeatedly, so these discriminators are derived from the entropy regularization. It means that we introduce the entropy of policy and state transition dynamics and Karabakh-Rival divergence of them. So in that case, we have two hyperparameters and we can derive the soft Bellman equation based on that, based on the normal Bellman equation with entropy regularization. But anyway, important message is that so during the training, so of the discriminators, so reward value functions are updated. Then, so as we did in the, for example, soft actor critic, so we can derive the similar update algorithm to improve the policy and model. So it means that so after learning the after training the discriminators, so we can get some reward function and value function as well. So, but so these are not complicated. So it means that we cannot draw samples from this distribution because R and V are kind of represented by neural networks. So therefore, it's not easy to handle. So therefore, we utilize these minimizations. So that is we introduce a Kerr divergence between these two distributions to map to the this energy-based representation to the neural network probability distributions. Anyway, so this is the most complicated part of the model-based offline model-based imitation learning. Then the third one is the generate trajectories. So after offline model-based imitation learning learns the policy and the dynamics, so it's possible to generate the trajectory, and then they are given to the evaluators. So since our method learns the stochastic policy, so we can generate a lot of variety of various trajectories. So, and also, so our method learns the reward function at the same time. So therefore, for each generated trajectory, so we can compute the total reward as a evaluation from the imitation learning side. So those information is used in the later step. But anyway, so this is very simple, but anyway, this is very simple. But during the experience, we found that so as opposed to the kind of learning from preferences in the natural language processing, so as ChatGPT did, so it's quite difficult for human evaluators to distinguish whether this behavior is superior to other behaviors, because so in this example, so the agent failed to continue to handover, so sometimes it drops the object. So in that case, so human evaluator can distinguish this, know that this is unsuccessful behavior. So this is successful behavior. So therefore, this is better than this one. But if human evaluator sees the two successful behaviors, in particular the robotic behaviors, so sometimes it's quite difficult to distinguish whether this behavior is better than this other one, because so human evaluator cannot access to the internal state of the robot dynamics or value function. So therefore, sometimes the decision is very ambiguous. So therefore, so not only show the demonstration, we provide the predefined scores at the same time to the human demonstrators, such as maximum torque, smoothness, and elapsed time during the demonstrations. Those information are used for human evaluations. And finally, so we did the reward learning from preferences. So actually, our method is based on the DLX. So it's introduced in the previous presentation. And so, but the important thing is that evaluator assigns the labels to the trajectories. So it can be interpreted inversely learning from preferences. So, but the important thing is that in this step, so reward function is initialized by the result of the imitation learning part. So therefore, we don't need to learn the reward function from scratch. And this is a kind of probability for using the evaluation. So this is already proposed in a lot of previous studies. But anyway, so we can use the cross entropy loss to train the reward functions. And finally, so we go back to the offline model-based reinforcement learning. So that is in this phase, so the reward function estimated at the previous step is copied to the model-based imitation learning part. Then, so if the preferred trajectory, if the trajectory preferred by the human evaluator has a smaller total returns, so there is a conflict between the human evaluation and the imitation learning part. So therefore, so it's added to the expert data. So that conflict data. So then, so we continue to update the value functions and reward functions and policies, something like that, in this phase, as we explained in the previous. Actually, this is all of my algorithm part. So then let's move to the experimental part. So we did two experiments. One is pick and place, that is a pick up and red and blue boxes and stack them. And second is the handover, so that the pick a red box by the left arm and hand over it. So this is the kind of architecture. So we use the two X7 manipulators. So X7 is a kind of 7 degrees of freedom manipulators, and on the tip of the manipulator, so in the effector, so 6-axis four-stroke sensor, RGBD camera, and gripper are mounted. As you can see, it's a bit hard to see that this is a torque sensor, camera, and gripper. And also, so we use a haptic device with force feedback. So the human subject can control two devices to control these two manipulators. So it has a 6 degrees of freedom force feedback. So it means that during the control, so the human subject also receives human force feedback. So those force feedback is quite essential in this kind of manipulation tasks. And sometimes, so this kind of force feedback it's hard, and human subject gets surprised. So when unpredictable force feedback occurs. But anyway, so since we consider the force feedback is quite important, so we use this kind of setup. And then, so we for each experiment, so for each task, so we collected 20 expert demonstrations. And then for demonstration provided by the machine learning part per iterations. Okay, so this is an example of the learned behavior. So left is after machine learning, but there are no real learning from preferences. So it means that this movie shows that this is just a result of the imitation, offline model-based imitation learning. So sometimes it can hand over the object, but this manipulators fail to continue to place the red object. But after imitation learning and you are learning from preference repeatedly, so red box is hand over, then so this light arm can grasp the object, then it successfully place the correct position. And this is the second example on the pick and place. So left figure shows left movie shows after imitation learning without real learning. So in this case, so right arm moves correctly, but left arms fail to control. So sometimes this kind of behavior observed because number of expert demonstration is limited. So therefore, and it tries to run some stochastic policy. So sometimes, so in a offline model-based image learning, so there are no interaction to find the policy during at the first step. So therefore, we often observe this kind of strange behaviors at the end. But after imitation learning and real learning from preferences, so it can learn to stack the pick and place object appropriately. So two arms are controlled simultaneously, then so pick the blue object and press it and wait. Right arm wait for 5 seconds, so pick. After place right arm control to place the object. So this is the experiment result. So we did 5 experiments for each task. This figure, this number shows the number of successful generation per 10 trajectories. So at first we show the result, but only demonstration is provided. So that is there are no real learning. So before learning, so for each task, so we obtain this kind of successful trials. But during the iteration, if there are some increase of the success trials, but sometimes the improvement is limited. But we score information such as maximum torque, smoothness, and elapsed time are provided to the evaluators. So these kind of number of success generation increases at the result of the iteration. So as you can see, so for pick and place and handover, so we can our system learn to good policies at the end of the learning. Okay, so anyways, but we have a lot of limitations. That is, as you can see, so we have to deal with a lot of noise in some sense. So one is that we have to treat the noisy human demonstrations. So in particular in the system, so due to the force feedback, so sometimes human surveys got panic. So it means that for example, so if human surveys control the manipulator, but he or she gets some feedback from the left arm. As a result, so he pay attention to control the left arm. As a result, so he failed to control the right arm at the end. So as a result, so right manipulator moves shows some strange behavior. So we observe that those behaviors are suboptimal, but we have to develop the method to distinguish whether this behavior is suboptimal or optimal. And the second part is that human evaluation is also inconsistent. So it means that even though same pair of trajectory is given to the evaluators, so human evaluation is inconsistent. So in that sense, so we have to handle with this kind of noisy kind of evaluation. So because our method is based on the kind of logistic regression. So and in the field of machine learning, so there are several ways to handle this kind of noisy level classification tasks. So now we are introducing those techniques to our frameworks. So finally, I'd like to conclude my talk. So today, we propose human in the loop imitation learning at first. So expert provides some expert data sets, and then imitation learning estimates the expert policy and its reward functions from the expert data set. Then estimated policy generates the trajectory with scores. Then human provides a binary evaluation and add some trajectory to the expert data set if necessary. It means that if there are conflict between the evaluation of the imitation learning and that of the human evaluators, so those are treated as a kind of a new information about the expert behavior. So then finally, imitation learning updates the value function based on the previous steps. And we showed some real robot experiments. So some important things that in this study, we did not use the simulators at all. So it means that we just use only real robot experiments. So this is quite important because in some robotic experiments, it's a very difficult to construct useful simulators from scratch. So therefore we are interested in this kind of data-driven framework, even though we utilize model-based approaches. Anyway, so that's all my presentation. Thank you for attention.
If you have any questions, please come up to the mic and ask. Also, the people on Zoom, you can ask. I can read out the questions. Thanks. Actually, I have a question. It's actually very interesting that you don't use simulators. And typically, I've seen at least these preference-based frameworks being used with human feedback. And the typical numbers that I've seen is like 1,000 to 2,000, depending on the type of task. So I was just wondering how many feedback samples you were able to achieve this kind of performance with?
Yeah, because so in the standard, you are learning from preferences, so your function is trained from scratch. Right. But in our case, so your function is trained at first the imitation learning, so just so it has a good initial real function, and in this experiment, so for each iteration, so 10 demonstrations are provided by the imitation learning by iteration. Then so we did only 3 iterations in this example. So it means that there are 3 opportunities to provide feedback to the imitation learning part.
In terms of the preference feedback, you mean?
Yeah, yes.
Oh, okay. So just 3.
Yes, 3 chances. Yeah.
Oh, okay.
So it means for each iteration, so 10 demonstrations are provided.
Right.
Then so combination of the 10 demonstrations are considered.
Yeah, that's still quite impressive, I would say. Yeah.
Yeah.
And I was just wondering, do you also take into account the humans' rationality in terms of giving the feedback? For example, some users may find one trajectory more preferable than the others, where there might be some exceptions where they find trajectory that's normally not preferred to be more preferable in that sense.
So honestly speaking, so because we ask many subjects to do this kind of task, but there are so many variations. So in particular, so if the subject is familiar with robot control or reinforcement learning issues, so they are very carefully control this kind of robot, and the evaluation is also consistent in some sense. But so if the subject does not have a strong prior knowledge on the robot control itself, so their decision is quite diverge. So therefore, as I said, so we need to introduce kind of techniques developed in the machine learning field to deal with the kind of unreliable label information. But even so, simple application is not helpful for improving this kind of performance due to the large variation of the human evaluation. So in particular, so as you can imagine, so in case of the natural language processing, so it's relatively easy to distinguish whether this kind of a sentence is natural or not. But in the case of robot behavior, so it's sometimes difficult and complicated to distinguish whether this behavior is natural or not, because so you have to distinguish robot behavior, not human behavior. You have to evaluate robot behavior. So in that sense, so even though robot behavior is optimal based on some criteria, so sometimes it's not natural for human evaluators. So in that sense, it's a very consistency. So therefore, we show some scores such as maximal torque and something, but we just show the scores. So the evaluation is dependent on the evaluators.
Of course, yeah. Any questions for our speaker? I was actually also wondering whether the decision to not use a simulator was a conscious one, or and if so, like, are you against the use of simulators, or is it just to make it more practical?
So actually in this study, so we did not do the simulator, so because we mainly focus on the issue of the variation of the human demonstration, the human evaluation. So sometimes, for example, so if we introduce a kind of simulators, so human demonstrators has to interact with a real robot system as well as the simulators. But so due to the gap between the simulator and the real robot systems, so it's quite complicated for the human demonstrators. In particular, so there are some force feedback in the robotic system. So in that case, there are very huge gaps. So we actually we developed a kind of simulator for this system, but it's totally unreliable. So therefore, we do not use the simulator.
Oh, yeah.
Okay. Yeah, thank you so much for your presentation. I just have a quick question. So do you assume that the demonstrator is the same both for the initial trajectories and then for the corrections? Or could we consider like multiple demonstrators with different preferences in terms of the trajectories and the things they want to see the robot doing?
Yes, thanks. That's a good question. And actually, in this talk, we assume that we is only one human subject, and it's consistent in some sense. But by combining this kind of multitasking intentionality, so it means that multiple demonstrators are included by combining these issues. So in that case, the formulation is a bit complicated, but in a framework, policy depends on the demonstrators, but evaluative dynamics may be independent of the evaluators. So in that case, our model, offline model image learning, successfully learn to model dynamics, but it also differentiates the human subject simultaneously. So in some sense, but it's a bit complicated, and actually, we need, even though we use multiple, for example, we have 10 demonstrators, so they are categorized 3 or 4 discriminate demonstrators in internal sense. So in that sense, we have to how we organize the demonstrators. So those are kind of future issues.
Okay, thank you so much.
Any other questions? If not, let's thank our speaker. Thanks. The next talk, we still have time for the next talk, so it's about 5 minutes away. So it appears the speaker is not yet here. So while we, I think we'll just wait for him. Oh, he's here. All right. I didn't spot you. Sorry. All right. So, okay. So our next speaker is Dr. Pulkit Agrawal. So Pulkit is a Stephen and Rennie Finn Chair Professor in the Department of Electrical Engineering and Computer Science at MIT. He earned his PhD from UC Berkeley in 2018 and has also co-founded Safely You, a company that builds fall prevention technology for the elderly. His research interests span robotics, deep learning, computer vision, and reinforcement learning. He has received a number of research awards, including the Sony Faculty Research Award, Salesforce Research Award, Amazon Machine Learning Research Award, Signatures Fellow Award, Fulbright Science and Technology Award, among several more. And more recently, he was also awarded the IEEE RAS 2024 Early Academic Career Award in Robotics and Automation. So let's welcome our speaker, Pulkit. No, you can just connect. Just connect.
start?
Yeah.
Good afternoon, everyone. Thanks for having me, and thanks for coming to the talk. So, I'll talk about human in the loop, robot learning, and the focus over here is going to be that what's the right combination of humans and automatic ways of learning robot controllers, right? And that balance, if done the right way, can reduce the amount of human effort required to create controllers for many, many different diverse tasks, right? And that's really what I would like to convey today, that we have to be, mindful of how that balance is created. And I'll talk about some of the work that we have been doing in our lab related with this particular problem. So, So, many of us, have this goal that we want to make a system that can perform any manipulation or locomotion task, right? And, for a long time, this is how most industrial robots have worked. And if you look at the amount of human effort which is involved in, putting up these systems, it can be quite large, right? Because you have to make these special jigs, so that this part comes exactly in the same way every time, right? Similarly for each robot, there are special mechanisms which are made. So it's not just in software that there's customization, but there's also customization happening at the hardware level, right? So these systems are great, they're very useful, but in context of amount of human effort and time which is required, it's quite substantial to develop such a system. Now, of course, we have moved beyond them, and trajectory optimization and model predictive control. These techniques have looked to reduce the amount of effort required in programming robots. And there's always this argument about should we make the hardware be very general? Because then, if I have to go towards different tasks, we don't have to respend the effort in designing the hardware again if the tasks we want to do are human-like tasks, right? And that's always been a big motivator for having a humanoid robot. Now, of course, there are many tasks. If you think about very fast pick and place, today there are delta arms which are used, and they're working at superhuman speeds, and that is the right form factor over there, right? But let's, for the sake of argument, it's not that I'm advocating we should necessarily have humanoids, but for the sake of argument that we don't have to keep on changing our hardware, let's just assume we have humanoids, right? So at least your hardware effort is once, and now the game is only a software game. Not entirely true, because there are always interactions between hardware and software, so I want to be sensitive to it. But given a good piece of hardware, let's think from the control perspective. And all of you have seen these videos, and these videos are amazing. These robots can do amazing things. But the challenge, really, in my opinion, is that it takes teams of people and time to write controllers for these different tasks. And therefore, this approach does not end up being as scalable as we would ideally like it to be. And so what I think the challenges which we are faced with is that we are spending substantial amount of human effort in designing these controllers, and even then the amount of generalization we are getting is quite limited. Right? For example, the videos you saw on the previous screen, they were really working in those particular environments, and it's unclear what is going to happen if we were to go to a more general environment. Right? And lastly, some of the tasks are just hard. Like, for example, doing things that humans do with their hands is quite challenging. Now, if we look for the same scheme that has been used in vision, language, and speech to solve some of these problems, right? Because these problems also existed in those fields. is to really collect data, right? So the equivalent of human effort in designing controllers was the human effort in designing features, right? The equivalent of limited generalization was the features which were defined by humans would not work across different problems. So you would have a SIFT, and you would have SURF, and you would have HOG, and the speech people would have MFCCs. So it will be a whole zoo of different features that we would end up having. And on some tasks, performance would be so low that those systems would not be deployable, right? So it's a parallel universe, once we are talking in the software space. So you can say, well, if the problems are the same, then we should just use the same recipe that was used in these different fields, and maybe that will reduce the human effort and also resolve these problems. But as we all know, that language and image data can be downloaded from the internet, and you can build a foundation model. But in robotics, we really don't have this data. So one approach is just go collect the data. And that is exciting, and there have been some very nice demonstrations. I'm showing a video from TRI, but there are other labs which have done similar things, where a person demonstrates a task, and robots are able to imitate these tasks, and we have seen these robots perform a wide variety of things. So clearly, we have made progress that designing a controller for a new task is intuitive for a human, but then again it takes lots and lots of human effort to collect this data, right? And I was trying to do some back of the envelope calculation. How are these numbers going to stack up, right? So if we look at GPT-4, it had around 10 trillion tokens on what it was trained. Now let's assume in robotics that one trajectory. Now what do I mean by a trajectory? Suppose you're doing pick and place. Let's say that is one trajectory. Now a lot of the data is also correlated. An average sentence in English is maybe 10 to 20 words. So let me assume similarly each trajectory is a sentence. It has maybe around 10 tokens, right? Now, if I have to collect 1 trillion trajectories, it's a lot of data to collect, right? I mean, even if I pay 1 to 10 cents per trajectory, it's going to cost a lot of money. Right? Now, the same philosophy did work in self-driving, to a large extent. It's still being played out. But, if you look at, some companies, they were able to collect this amounts of data because, driving is something that people already do every day. It's a necessary thing. You do it, you can collect data, and therefore it's not really a problem. But right now, we have to instrument the human environment to collect data. It's not as natural. Teleoperation is quite slow. So therefore, it wouldn't be the case that people who are working in factories or working somewhere else will suddenly wear some special glove and start doing it, and the speed remains the same, right? The speed is quite slow. And when the speeds are slow, then you can't really do it in production, which means that you'll have to pay someone, right? And I think, it's an exciting research topic, how you could develop a nice exoskeleton or a nice teleoperation system so that you could repeat the self-driving story, right? But we really don't have that kinds of teleoperation system today, but it's definitely an exciting area to research on. But till the time we don't have it, this number is quite large. Right. So what do we do, if we are faced, with this number? And this number is just quantifying the cost of humans, right, in some way. So as the topic of this workshop is, how do we reduce, or what's the right role of humans in robot learning? And, this is a number I would put. Now, again, this, don't, it's not, don't read too much into this number because, it's assuming we need the same amount of data as GPT. Maybe we need more, maybe we need less, right? But it's a ballpark. Now, the one thing which is special about robotics, which is not necessarily true about language, is that language, cannot really be simulated. It's not governed by the laws of physics. It's there, and it's there. I somehow can't write down rules by which I can generate language. But that's a difference between robotics and language, I would say, because in robotics, it's all about physics. When it is all about physics, we can write on a simulator, we can say what is going to happen next, and potentially generate large amounts of data. Right? So if we have this capacity, then why don't we try to leverage this and then try to train robotic controllers? Right? And of course, the argument is going to be that, hey, simulation is approximate, so is it going to really work? The work in recent years has shown that the sim to real gap can be bridged to an extent. But even if you were a purist and you did not believe in simulation, I hope you do believe in pre-training, right? So in that case, training in simulation would just be powerful pre-training that you can leverage to then tune your robots in the real world. Right. So in order to reduce the amount of human effort, because of the reasons I mentioned, we placed a bet on trying to leverage simulation and see how far we can push it. And the pathway really looks like that if we can leverage the simulator to design complex and generalizable behaviors, or let me not call it generalizable, let me say design complex and robust behaviors quickly, and we can design many of them, then we can put them all together into one model, which you can then call the foundation model for robotics, or at least for sensory motor control. But the key missing piece, when you do end up going to simulation to design controllers, is it takes a lot of effort to design these controllers. And I would like to quantify the human effort of these controllers in two particular ways. And we are going to look at some applications in locomotion and manipulation. But first, let's look at what causes a human effort to happen. So the first thing the human has to do is to design the cost function, right? Which is what I'm representing by J. It's evaluating a sequence of actions which are being taken. And we have to perform this optimization subject to some constraints, the constraints from physics. Now, typically, performing such an optimization when we use the full physics ends up being quite challenging to do. Because many of these problems end up being continuous discrete optimization problems, hard to optimize. So typically, humans come into the picture and they design what we call as reduced models or simplified models. So for example, my cost function might be quadratic. I might linearize my dynamics. Now this becomes our beautiful LQR control problem. Then we can solve it. Of course, this is one reduction, and many such reductions exist. So, these things are, easy to, optimize. But the problem is you need to keep doing this reduction for every problem that you're encountering, right? And that ends up being a challenge or where the human effort is being spent, right? So just to put it in context, if we are trying to do, say agile and robust, legged locomotion, there are different kinds of things we have to face with, right? For example, things like variable friction, the softness of the terrain could be different. The geometry of the terrain could be varying. You might be going up or down the slope. If you're trying to be fast, then you might hit the actuator limits, which can cause non-linearities in your optimization. Then again, if you have high forces, these can damage the motors. If the robot is in the air, if you move your legs, it is very different, the dynamics, as it would happen if you were on the ground. So you really have different regimes under which we are doing optimization. And all of these really add to model complexity, right? And so trying to deal with all of these things together, ends up being infeasible, for the reasons that we, just discussed. And the human comes in and they say, okay, let me make some simplification. So some simplifications might be, I'm only going to deal with variation in softness, but other things are going to be held constant. Or I'm only going to deal with high forces, other things are going to be constant. Right? So this, simplifications are, performed, task by task. And also in what kinds of operating conditions my robot is going to be working in. Right? So, due to, this model simplification step, not only this is hard to scale, but also you may not be able to fully leverage your hardware and may not be as agile and dexterous because you're really operating under a simplified model and not leveraging the full physics, which is out there. So an alternative is to take the full model, right, that we have and really learn from the full model, right? And the way we're going to do this is to directly collect data with this full model. And if we can do it, we can solve the scaling problem, but also really make better use of our hardware. So instead of using more powerful optimizers like first order, second order methods, which require such simplifications to be done by humans, we're going to use something which is more simple. In some ways, there's a 0th order approximation, which is collect large amounts of data and then directly train a policy without necessarily simplifying the physics, which is there. Right? And that's really the philosophy, in my opinion, of why one should consider sim to real learning as a way to actually reduce the human effort, which is being put in to designing controllers. So what we're going to do is to have one policy which is going to deal with all of these different variations, and this is going to be trained with reinforcement learning. And this line of work has been pursued by different labs, and it's quite common nowadays that we would train locomotion policies in simulation where large amounts of data is collected, and then we can deploy them in the real world. And I'm just going to show you a few demonstrations of what we have done over the past couple of years. So here's an example where we were able to leverage this hardware to break the speed record on this particular platform. If we put oil, for example, on this whiteboard, the system ends up being robust. So we can get both the agility but also robustness in the system. Here's an example where the quadruped is walking along, but one of the screws in the motor becomes loose. So what you find is that it starts limping, but it continues to walk. And the reason this happens is because in simulation, we have varied parameters such as motor strength, so it is able to learn from it and adapt when the same thing happens in reality. Now, once we can start doing walking, we can make the task be more complex. So over here, the robot is, using 3 legs to balance itself and uses a 4th leg to kick a soccer ball. So it's both fun, but also a more, challenging task to perform. If the robot were to fall down, it will get up. And the thing is, now you don't need to design these different behaviors, in a task by task basis, right? We are using the same code base to be, to design these behaviors without making, simplifications which are at the task level. Then, after, one can perform, dribbling of soccer ball, you can also think of the additional arm as a 5th leg that you can put. And, what this is demonstrating is that you can increase the reach of the robot to be doing, to go more where it wouldn't be able to do if the base was fixed. Then, if your robot is able to reach to different places, then, if the Apple Vision Pro came out, you can build an interface by which you can then control the robot to perform, different tasks. And, then, what we started looking into is, not only it is important to control the positions of the robot, but also the amount of forces which are being applied. One that is needed for more forceful tasks, but also the compliance, helps robots being safe around humans, right? So, instead of just doing, position control where we are going to input the target positions of the end effector and the target velocity, we're also going to input the desired force that we want the hand to be exerting. So this is how our task representation is going to be. And then there's a joystick by which you can control how much force you want. And as you're moving the joystick, you are controlling the location of the end effector. And we can train these things by emulating a virtual soft contact. Now, once you perform such training, what you notice is the system becomes compliant. So now as Tiffany is moving the robot, it is demonstrating its compliance in this full workspace of the robotic system. Now here Gabe is kicking it, but what we're doing is varying the stiffness. So what you see is different stiffness levels. Over here, we are trying to see how much force the robot can apply. So what you see is the robot uses its knees to change its orientation so that it can increase the amount of force it is applying. And we can do this impedance/force control in a large workspace, and this task of pulling the chair was demonstrating this particular feature. And then even if I'm sitting on it, this system can perform the task. And then on the safety aspect, because now these systems are compliant, they also end up being quite safe. So what I was showing through these videos is the ability to leverage simulation, which another interpretation is to reduce the human effort in doing model simplification, but yet achieving good performance. And now we can take the same philosophy that we have used in context of locomotion, but also apply this in context of doing dexterous manipulation. Right? So beyond picking objects, there are many things which a human hand ends up doing. And a common feature for many of these tasks is you pick up an object, but then you make the object move relative to your hand. So we can again leverage simulation to train hundreds and thousands of robots in parallel, for example, to reorient these objects. And we can see how these systems end up working in reality. So here's a camera looking at this 4-finger manipulator, which is trying to reorient the object from the current configuration to the one on the top right. And we chose these shapes because these shapes are complex. They are not convex or smooth. They have a geometry which is not easy to model. And if you look at what the system ends up doing, it reorients the object to the desired configuration, and then the hand moves, showing that the object is held stably. Now, the system is not perfect. It makes many mistakes. So this is just a demonstration that we are able to control multiple fingers on new objects that the system wasn't trained on, but there's still quite some work to be done to make it robust enough for any practical deployment. So now that we are able to perform this multi-finger control, we can go to other fun tasks. For example, rotating this vegetable so that we can peel it. So the hand rotates it, gets it to a position where the unpeeled part is facing, and then as it is applying forces, see how the hand is resisting all these forces. Right? We don't have any touch sensors, so all of this is happening purely through proprioception. Right, and here's another vegetable, that is being rotated. So trust me, if you put a cylindrical vegetable, it's going to work. But if you give it a ginger, it isn't going to work yet. But that's something which will come in soon. So as a summary, until now, what we have looked at is how we can design agile, dexterous, and robust behaviors for a single task in context of dexterous manipulation, locomotion, and locomanipulation. Right? Now, what we would like to do is that now that we have this paradigm by which we can design multiple controllers, we would like to scale to many tasks. Right? And if we can do it, then we can train this large multitask model. So the question we can ask now is, okay, let's go ahead and scale it, but it's not that easy. And let's look into why is it still not easy to scale. So, as a reminder, there were two things that we were, discussing where human effort is involved. One is in designing the cost function, other is in doing model simplification. So we looked at the first aspect, which is we don't have to do model simplification anymore, right? But when people are doing sim to real, what do you think most people end up doing? Anyone? domain randomization, that's part of the answer, right? So, people end up doing, reward and environment design, right? So you keep on designing, different reward functions. You have to still set up your training environment. Right? And this is, what we are going to look at next. How do we simplify environment design? Now, what do I mean by environment design? So simulator is something which, runs the rules of physics, but someone still has to import the assets, arrange the room in this way where these chairs are all kept in a particular position. Or if you want to emulate your kitchen, you have to still arrange things in the right way. So that is still quite some effort to do it and to get those CAD models be imported. Now, there is a line of work happening where people are scaling up these online data sets with CAD models, but we still don't have a big data set of scenes which are available that we can download and which are realistic. Right? And the other thing we're going to look at is how we can simplify reward design. And both of these perspectives, I'm going to talk by leveraging a human in the loop to help us solve these problems. Okay. So first, let's look at environment design. So the way we have been thinking about designing the environment is, imagine that I want to put a robot in your house. What if instead of trying to write a program which would generate a simulation environment to mimic your house, why not just have a human come take a scan of your house, right? And this we can start doing because of the advances which have been happening in computer vision and things like NERF. Right? So once we take a scan, this is how a scan might look like. It's not perfect. Still there is work to be done. And once we get the 3D parts, then we have to still add articulations. For example, the door of the microwave can open. Some things can move in particular ways. For example, drawers can also slide through. And here is a timer that we have put to kind of record how much time a human is able to take. And we build this API, right? So for example, over here in 4 minutes, we can complete this task of doing the scan and adding articulations to a few joints in the scene. Now once we are able to do it, then we can start training in simulation. For example, to open the microwave over here. And once we can train in simulation, then we can go, deploy these policies in the real world, right? So I think by having a human, convert the real world into simulation, we can, scale, simulation to environments which can be quite complex. And on the way, we are collecting data because we are labeling all the articulations so that this process can become more and more automated as we go in the future. So here are some more examples of the same paradigm being applied to different tasks. So on the bottom, you're seeing the scanned versions of the environment. Sometimes the rendering is a bit different because we do randomize the rendering. So over here is a digital twin trying to pick up the cup and throw it in a trash can. And here's a real world deployment version of performing the same task. Now because we have trained these things in simulation with large amounts of data, we do get a certain level of robustness and generalization. So for example, here the cup is being picked, it has to be kept over here on the bookshelf. And what you can see is, Marcel is moving things around in the environment, yet the system is robust. And the mug will hit the book rack, but it recovers. The robot keeps the mug again. We can, disturb the mug, and the system is going to follow the disturbances. But again, the only reason this is happening is because we are able to collect large amounts of data in simulation. So we hope, with this human in the loop approach of trying to, generate these simulation environments, we can today go to complex environments and try to train robotic systems. And then on the path, collect enough data of, humans, labeling these articulations that in future, this process can also become, more and more automated. And now I will, switch gears and, talk about the other complementary aspect where humans are involved, which is, in trying to simplify the reward design problem. So, going back to our picture, and there were two arrows when you begin with. One was, to simplify models or building reduced order models. We took care of it. Now we are going to try to figure out how we can simplify the design of cost functions. How much time do I have? Maybe 10 minutes?
Yeah, around 10 minutes.
Around 10 minutes, okay. And I'm going to present work done by Max and Marcel, and this is in collaboration with Abhishek Gupta at University of Washington, and I'm using some of his slides over here. So if we think about what do we really care about when we are doing reinforcement learning, right? This is a typical RL agent loop where we want to maximize the sum of rewards, and and the human is trying to specify a particular reward function. Many times we have trouble specifying the reward function. The agent does something bad. We come back and we modify the reward function, right? And that's where this loop ends up being, right? Which is your reward or the task specification problem. So sorry. So in some ways, the human is going to provide either a piece of code or some data. For example, the data could be demonstrations. There's some things the human is generating, from which we are trying to infer the reward function. And this reward function is going to train the RL agent, right? This is basically, what is happening. And the question we can ask is, how is it that the human should define this reward, right? In the sense, what is the data the human should, provide? And what are the algorithms that we should use to leverage that data to come up with a reward function? And there have been different approaches to this problem and different ways of thinking about it. But fundamentally, let's try to understand what is the purpose of a reward function, right? The reward really has two purposes. For example, if you think of this green guy wanting to go to this red square over here, right? The reward should provide what success looks like, right? And we hope we can just work with a reward which is success, but these sparse reward problems end up being quite challenging. So a second desired property of the reward is, can you also guide me towards getting to the goal and not just only when I reach the goal? And then let's look at the first part, which is how do we identify that we have been successful, right? And many times the goal is to reach a successful state. Now, if the state is low dimensional, if the state is low dimensional, for example, reaching over here, we can compare the distance between states, and this problem is quite straightforward, right? But if the state is not expressed as an XY location, not as a low dimensional state, but as an image, doing this comparison can be quite challenging. Now, this is one place where vision language models, have been used, more recently to provide their success criteria. Right. The other thing is, how do I, end up, guiding the system towards what's a useful direction to make progress. So we talked about the first criteria that we want to measure success. That's not, straightforward from high dimensional observations. Vision language models provide, one way of potentially doing it, but they're still not working everywhere, and the rewards that they provide can still be noisy. So one thing which we'll come down to is, how can we have human in the loop to help with this process, right? And the second point where we want to use the human is to guide the agent's movement towards a goal. Now, typically, when we are doing reinforcement learning, the exploration is quite random, right? So we end up taking a bunch of random actions. Suppose this is the environment in which the agent has to move. These are the actions it is taking. So if you do random actions, you are bounded in some ways, right? And what we want to do is, instead of taking any particular action or any random action, you want to move towards the frontier. Because if we can move towards the frontier, we can end up exploring more. And frontier-based exploration is something which has been discussed a lot in the literature. But the challenge again becomes is, if you look at the frontier, you can go anywhere in the frontier, right? Going anywhere in the frontier is also not that useful. For example, if the goal was over here, you want to move in the frontier only on this side. Moving on this side of the frontier is not going to be advantageous, and we are still going to lose a lot of data. So where a human can come in very naturally is to provide very sparse supervision on what frontier should we explore and what frontier should we not explore. Right? And that's pretty much the main intuition we are going to bring in for the human to be able to specify what frontier state should the agent be exploring. So how is this going to work? One way where humans define how to go beyond the frontier is to do reward shaping. Right? That's one method, which will end up defining a reward function like this, essentially. In these 2D examples, it is somewhat easy to do reward shaping, but generally speaking, reward hacking is a well-known problem where your dense reward can actually hurt and cause the agent to do things which it should not be doing. Right? The other thing we can use is humans in the loop to help us figure out if we are making the progress in the right direction. Right? And the way this is going to work is the following, that if I have two states, for example, over here and over here, I can simply ask the human which state is closer to the goal. Right? And based on this response, we can train a distance function, right, which says, or a reward function, by leveraging these preferences, pretty much like how people learn reward functions in RLHF, right? And this is inspired by the work of Cristiano 2017, where they were using preferences on trajectories to figure out a reward function. Right? Now, the good news over here is that we are not doing reward shaping anymore in the way of writing a reward function, but it's a job which is much more intuitive for a human to perform, which is, hey, am I close to the goal or not? Right? So even a layman could potentially do it, and therefore we can scale it up much more, and it doesn't require an expert human to perform this task. Right? So it's simple and easy to scale, no information is needed. But the moment you start scaling it up, the problem becomes that human preferences can also be noisy. Right? So if you are learning the reward function based on preferences, the rewards can end up being noisy. And if you do this naive way of getting a reward function based on human preferences, the noise can be large enough, especially if you run experiments at scale. For example, what we did was, we created some, toy environments, put them in the virtual world, and had naive users across the world come in and provide these, reward these preferences. And then you can notice that these preferences end up being noisy. Right? So the question then becomes is, how do we, deal with the noise which is being injected into the reward learning scheme? And the main idea is, don't try to learn the reward function from human preferences. Just figure out, where in the frontier should the agent go, right? So only, apply the preferences on goals. Don't get a reward function. Now, how does this, end up working? This ends up working in the following way. That, suppose the agent is, able to go from this point to this point, and this is where it needs to go, which is the desired goal location. Now, along this trajectory, we are going to have states, and these states are going to go to a human, which is going to say which state is closer to the goal. And based on this, we're going to learn, actually, a classifier, which is going to say, well, this goal is closer to the desired goal. And now, once we are over here, we're going to perform random exploration, which is going to expand our frontier. Right? So because we are just putting a preference on the goals, even if the goal labeling is noisy, at the end of the day, you're just learning a goal condition policy on a more diverse distribution of goals. So you're never really learning the wrong thing, because the noise and the rewards is not being propagated into your policy. All that is changing slightly is the distribution of goals on which you are training. And if you have a model which is complex enough or as powerful enough, this noisy goal distribution should not affect your training so much. And that's really the reason why we are able to deal with more noisy reward. So the way this process works is, here's a robot, learning a goal condition policy, which, goes into a data set. Then, on this data set, we have humans who look at, some of those goals which are sampled, right? And then they're going to provide supervision for this goal selector. And these humans can, come in, whenever they want, because the agent is always running a goal condition policy depending on the states it has visited. And once in a while, a human can come in and say, okay, this goal is better than the other goal. So you're not dependent on the humans for learning, because you can still keep on learning a goal condition policy. And once in a while, the human can come in and express their preference, right? So this is the UI that we ended up using, where we end up showing two states. Here is a task, and ask the human which state is better, right? Okay. Let's see. I'm going to move forward, and then we can use this preference-based goals to perform a variety of tasks. All of these tasks are in simulation, and based on what I showed you before, the hope is all of these things are also going to transfer in the real world, right? So here's another example, where we were trying to have a robot pick up this piece of cobble, place it, and this is showing the amount of training steps which are happening, right? So what the robot is doing is initially it has a policy to pick up an object, right? And then it can it can place it in some location which is close by, and then it takes a bunch of random actions. Now you can take all of these states that you get by performing this action, learn a goal condition policy. Now the question becomes is, what are the states that the agent should choose to explore? Right? Now typical wisdom would tell you go to the frontier, but the problem is where in the frontier you should go. This is what the human supervision is telling you, and you keep on making progress on the frontier. Right? So I let these videos play, where on the bottom the goal was to design this U, and on the top it's picking up towels and placing them. So now what we can do is with this paradigm we can really leverage humans around the world to be providing rewards, and we can deal with the fact that these rewards can be noisy and human preferences can be noisy, but we can still do learning to happen. So we did scale the system to multiple countries, and collected data at a large scale. And even when the number of labels were not very accurate, even with less than 65% success on how good the labels were, we can still end up learning. So this described one particular way in which we can try to make the design of the cost functions be easier. Right? And then the other perspective that we have been using to make this design be easier is as following, which is complementary to the first one. The second one is that if you express the reward, typically we express the reward as a task reward plus lambda times some auxiliary reward, right? And lambda ends up being a tunable parameter. And the auxiliary rewards are put in for different reasons, right? To assist exploration, to robustify the gate, to reduce the sim-to-real gap, so on and so forth, right? And typically, designing these rewards is tedious, but also tuning this parameter is quite tedious. right? And humans are simply not good at it. So the question we have been asking is, can we automatically tune this parameter lambda? Right? And really, I mean, just to give perspective, right? This is the reward function for trying to run fast. So you would ideally only like to specify the task reward, which says that run at a particular velocity in x, y, and a particular velocity at which the robot is rotating. But in practice, the reward functions have many more terms. Some for stability, some for minimizing energy. And this is not just one paper, but if we collect a bunch of sim to real papers, you see all these funny numbers and funny equations which are there. And the human just put in all of this time to come up with these terms and these coefficients. Right. So, oops. I don't have time, right? Probably I should stop.
Yeah, we're almost out of time.
I'm probably out of time. So, what I want to tell you is that there are ways in which you can tune this lambda automatically. I don't have time to describe it, but the idea ends up being that we learn two policies. For example, if you want to balance two objectives, speed and energy, we have one policy trying to optimize speed, one policy trying to optimize energy, and we make these policies compete with each other. And this competition allows us to derive an analytical update rule for lambda. And what this enables us eventually is to simplify the reward function. For example, we can just have the task reward and the energy reward and forget the other terms in the middle, and tune this lambda using a tuning algorithm which I do not have time to describe. But if you are interested, this algorithm is described in this paper, Redeeming Intrinsic Rewards via Constrained Optimization. And once we do it, we can still get quite agile behaviors. And this work was led by Srinath. For example, over here, it runs forward, it turns quickly back. And because we are doing this optimization not by doing hyperparameter search, but by using a principled method, we get these interesting emergent behaviors where if the velocity of the quadruped is set to 0, it actually squats down because this minimizes the energy consumption. Right? If it was standing, it would consume more energy. Right? So there's another example where we make it run, but then we say stop, and it would squat down, right? And a purely emergent behavior. And we did these comparisons where we were trying to balance j of pi and e of pi, and you can do an exhaustive hyperparameter search on lambda. The peak velocity we got was around 2.12, but with the algorithm IPO, which we developed, we can get a higher peak velocity. So we can do better than a rigid hyperparameter sweep because our algorithm dynamically adapts lambda during training. Right? And with this, we again hope the human effort which goes into reward design can be reduced. And with that, I guess I told you how we are augmenting the human ability to train with robots by developing stronger algorithms, which are not just doing better optimization, but are also accounting for the fact that when we get human supervision, that is noisy, and how to deal with that noise. With that, I'm going to stop and happy to take any questions.
Thanks a lot, Pulkit. Any questions?
Thanks for the very interesting talk. Related to the middle part, the breadcrumbs to the goal, how do you get around the ill-defined distance metrics? So comparing 1 meter to 10 degrees error, for instance, is that just all lumped into the uncertainty and errors that the humans make anyhow?
Yeah, so I guess we are not explicitly, trying to compare, meters and degrees because you have a learned, distance function. And it's really trying to capture the intuitive semantic space of humans in how they figure out their goal is closer or farther away. And the semantic space can be inconsistent. And that is what shows up as noise in the preferences. And that is what we try to be robust to, because we don't just use the reward function, but all we say is define a sampling distribution on the goals. So that noise gets reflected in the sense that sampling distribution becomes noisy. But you still learn how to reach those goals. And if you have enough signal, the sampling distribution of the goals will end up going towards the actual goal. So that's the intuition.
Hello, incredible work, and congratulations on the award. I would like to ask, you said that there's a lot of robotics data, which is true. We have for large language models, if we have for vision. I was wondering, is it the case that we could just leverage LLMs and VLMs with physics and simulation to acquire all the robotics data we would need? Or is there like some fundamental limitation that makes this not possible?
I think it's a good question to be thinking about, and I definitely know teams and labs which are trying to extract as much as possible from LLMs and VLMs. I think in my opinion, it's a different level of problem. For example, LLMs and VLMs are quite good at maybe doing high-level planning, but when it comes down to saying what are the forces that we're applying, or imagine that you have a screw that you're rotating with your hand, but you can't really see the screw because once you're inserting it, it is not really visible. So in many of these situations, VLMs cannot really help you, right? What they could tell you is, okay, here is a sub-goal that you should go towards, but what are the forces which need to be applied to go to those sub-goals, are not very apparent. Now, what you could imagine is that these LLMs and VLMs can make your long horizon problems with shorter horizon, which is what they're doing. And that can substantially reduce the amount of data which is required. You can use these models to help reduce the amount of human effort in reward design. So definitely they're useful ingredients of an overall solution, but I don't think they have it in them to give the low-level control signals.
Thank you.
Any other questions?
Thank you very much for the talk. I have a question about the simulation. At the beginning, you told us about, well, the huge number of data used in other contexts like ChatGPT. Obviously, I'm guessing here that you are not running that amount of simulations, but I like the idea of using this as like a pre-trained model. So in that regard, how much effort is needed beforehand in terms of running simulations to be able to have a good enough pre-trained model?
Yeah, so I think it's good to think about where are the places where the effort is being put in. So there are two phases, right? One is that you set up the simulation. In this study, you have to put in the assets, you have to design a cost function, then you have to let your algorithm run, you do some hyperparameter sweep on the algorithm. So if you look at how long are we running the algorithm, right? For the most of the locomotion work I showed you, we are running from maybe 3 hours to 12 hours, right? And 3 hours is roughly worth 100 days of real-time data. So you kind of get the context in how much data is being generated. But I think the more substantial time investment is happening in doing the hyperparameter tuning, doing the reward tuning, doing the environment tuning. But still to go from saying, hey, I have an idea, okay, let me imagine that I want to make this video where one quadruped is running, the second one jumps on top of it, and then they both jump together. Let's make a double quadruped parkour. Right. Now, in theory, I think this can be done. It's just that it will require, to get a good production, maybe 3 to 4 months of time at this point for us to get there. And I think that is what we're trying to reduce from 3 to 4 months for it to become 3 to 4 days. Right. So it's not the compute that I think we are bound on. It's mostly the design part that we're doing around it, which we are bound on. Once we fix that, then we'll become compute bound, right? So we'll get there, just not yet.
Thank you.
So if there are no more questions, I think we're over 10 minutes over time, so we'll just break for now. But please do come back at 4 p.m. We'll have a panel discussion as well, and that'll give you a lot more opportunities to interact with the speakers, and yeah, we'll see you then. Thanks.